All right, so we're going to start out looking at some exact models. By that we mean the models that fit perfectly to a scenario. So if I give you a certain scenario, you should be able to create a model that fits perfectly. All right, so we want to create exact models, and that's going to be um, based on a couple of things. All right. Now, what I will do is I will either give you the model or I'll have you create it. Now, if you're going to create the model, or if you're given the model, you're going to have to identify what type of function it is, what type of situation we're in. Are we in linear, exponential? Are we in quadratic? Are we in rational cases? And then if we don't have, if it's not something, it's not a type of exact model that we're absolutely given, then we're going to see how we can create the exact function. All right. And that just basically means, plugging in the right things and so on and so forth. All right, so let's take this example. Let's say a shirt sells for $10. So give a model which shows the total revenue depending on the number of shirts that are sold. All right, so the number of shirts is our variable here, and we want a model. So I want you to do two things. I want you to try to think about, you can push pause on the video, think about what type of situation we're in. And also, after you figure out what sort of situation we're in, create the model. All right, so push pause on the video and do that. All right, so hopefully you see that since we are selling shirts for $10 and that never changes, every time we add a shirt, every time we sell another t-shirt, we add another $10. So we're sort of adding repeatedly and repeatedly over and over and over again. So this is going to be a linear model. Okay, so the model we're going to get is linear. And I know that linear models tend to look like f of x equals ax plus b. All right. In this case, we're talking about revenue. So sometimes we write r instead of the f. So revenue is equal to, well, we don't start out with any revenue. So b is 0. I can ignore that. So this might be a 0. And if I'm talking about number of shirts, well, again, number of shirts here is going to be my variable. My a value is going to be 10. And the revenue is going to be 10 times x. So if I take 10 times the number of shirts that I sell, that's my total revenue. All right, so it's a pretty straightforward example in that case. Now, every time that we get a function, the reason that we're trying to do these modeling, the reason that we're trying to do this is so that we can answer questions about the situation at hand. So we can ask ourselves, like, how much revenue do we get when you sell 32 shirts? Or how many shirts do you have to sell to get a revenue of $450? All right. And these are basic, just straightforward function ideas. So it says, how much do you get when you sell 32 shirts? Well, remember, the number of shirts is my x. So the revenue when I sell 32 shirts is 10 times 32. So the revenue is $320. All right. That's fairly straightforward. And we can ask sort of the inverse question of that, saying, well, how many shirts do you have to get to have a revenue of 450? So instead of the r of x, you insert a 450. is 10 times x. Divide both sides by 10. And you would have to sell 45 shirts to get that revenue. And there you go. So not only are we going to have to develop models, but then we're going to have to answer questions based on those models. So here's what I want you to do. Let's pretend that I'm trying to retire and I start with $10,000 and I add $5,000 to that every year. What type of function, push pause, decide what type of function you're dealing with and build the actual model. All right, hopefully you've done that. This is, again, a linear function, linear. And, well, if you're going to build the model, I guess we'll call F the amount I have. X is going to be the number of years after the, I'm starting with 10,000. So if you're starting with 10,000 and adding 5,000 each year, we tend to write that in one of two ways. So start with 10,000 and add 5,000 every single year. So 5,000x. Or you could have reversed that and said take 5,000x plus 10,000. And either way, you're getting a linear model, just which piece you write first. Okay. Now go ahead and answer these two questions about how much you have after 10 years, how much you have after 30 years, based on the model that we had earlier. Or excuse me, the model that we had just a second ago. All right, so hopefully you've done that. Basically, I'm going to skip to the chase. If you put in 10 years, that's your X. Then you're taking 5,000 times 10 plus 10,000. You get out 60,000. So after 10 years, you'd have 60,000. And this was in dollars. We were taking $5,000 each year. We're adding to 10,000. So that's what you're doing. Now, after 30 years, again, all you're doing is plugging in 30 into your F of X. Well, that's going to end up to be 160,000. I'm not going to do the calculations on screen, but again, put 5,000 times 30 plus 10,000, you get 160,000. All right, let's take another example, and I want you to see what type of situation, what type of function we're in, and also create a model that describes it. All right, so if you start with $10,000 and you grow by 20% each year, well, you're multiplying now. And so the amount you're going to have, I'll call that the f of x. Since it's growing by multiplication, this is going to be an exponential function. And remember how exponential functions work. It's a, well, that's our starting amount, 10,000. And I grow by 20%. That means I'm multiplying by 1.20 every year. So x will be whatever the years are. Now this looks very familiar, should look very familiar, because this is sort of the interest model, right? A growth of 20% is not that off from the interest model that we talked about earlier. All right, so I want you to answer the following two questions based on %, I believe. Based on the previous model that we've built. All right, so hopefully you've done that. And what I got was that if you plug in 10 for this, you get about 61,917.36. I'm rounding it to two decimal places because of obviously the dollars and cents idea. So after 10 years, you'll have pretty close to what the person who added $5,000 per year made, right? After 10 years, the linear growth had about 60,000 as well, a little bit under. Now, after 30 years, you're going to see a drastic difference, in fact, of the previous example. After 30 years, I get, well, this is 2,373,763.14. All right. By the way, this is sort of a reiteration of the difference between linear growth and exponential growth. And you see here that even though linear growth might start out quicker, eventually the linear growth catches up. And in fact, this case, the exponential growth catches up. In this case, the exponential sort of catches the linear growth after 10 years. And then after 30 years, the exponential is just much, much bigger than the linear was. All right, let's take a look at this. We haven't said this too much before, but all right, I've said it a couple of times, but we haven't made it an explicit equation. So if a ball is shot straight up into the air at 5 feet per second, how do you model its height? All right, and I think I screwed this up when I was inputting this. This should have said, I believe, 50 feet per second. So let me, I should have had a 0 in there. If you do 5 feet per second, that's very, very slow. So let's do it at 50 feet per second. So I shoot a ball up in the air. Maybe I have I don't know, maybe I throw it. Maybe I have some sort of a launcher that does it. I launch it up in the air 50 feet per second, and I want to model its height. Now, it turns out I've said that this is going to be a quadratic idea earlier, that the height of a ball thrown up in the air is going to look like this. So we're going to have height over here and then time on the y-axis. So over time, the ball raises and then gravity takes over and pulls it back to Earth. All right. Now, this is what I'm trying to do here. I'm trying to transition us from actually coming up with the function on our own to actually looking up the function somewhere else. Okay? And there's a lot of places you can look up this function, but you can just go on the internet and say ball height versus time, and you might come up with the actual function. Okay, you can just look this up through Google. Now, I encourage you right now to pause, look it up online, and then come back and write it down and see what you would get with 50 feet per second, what type of a function that would look like. And by the way, in this scenario, what we're going to do is we're going to shoot it up from the ground level. So we're going to pretend that we have some sort of a launcher sitting on the ground, and at time 0, this launcher shoots it up at 50 feet per second, and then it comes back down. Okay, so pretend you start it at ground level. You start at height of 0. And again, I want you to push pause, look it up, and then come back and see what you get. All right, so hopefully you've got this. And let me just write it down. If you look up on the internet, you'll see something, and hopefully you got to a place where it said something of this nature. S of t, or height of t, t here is time, okay, is equal to negative gravity constant t squared plus your initial velocity times your time plus the initial height, okay? So, by the way, this gravity constant is either going to be in feet or meters. And if you're using meters, you use negative, or use the 4.9, so you get a negative 4.9 up front. If you use feet, which is what we have, then you're going to use negative 16. All right. So here's what our equation should look like. It should look like, well, this says S. I might write an H for height. Height after time t is equal to negative 16 t squared plus my initial velocity, 50 feet per second, plus my initial height, which is 0, so I can leave that off. All right? So this is the equation I got. And again, this is a very different way from coming up with it on our own. You know, here we looked it up on the internet, or hopefully you looked it up on the internet, or other ways of finding the equation. All right, so we have this idea, h of t is equal to minus 16 t squared plus 50 t. And then it says, how high is our object after 5 seconds? Okay, so what you're going to do is you're going to plug in 5, because again, t is time here. And then it says, how high is the object after 15 seconds? So plug in 15 into the equation. All right? And you're going to get a height in feet here because everything is in feet per second, or feet per second squared. So I want you to do that. Plug in those things and see what you actually get. All right, now, interestingly enough, if you take these, well, after 5 seconds, plug in negative 16, take 5 squared plus 50 times 5. I didn't actually expect to get this out the way I got it out, but if you look here, you should get negative 150. Now that's kind of an odd thing to get. And by the way, you get a negative when you plug in 15 as well. All right, and that's negative 2,850. Okay. Now, what's actually mean, or did we get something that was really bad? Well, here's what's happening. All right. On our XY axis, we're shooting this ball up into the air, whatever the projectile is. And starting at 0, after a certain time, it's going to come down, it's going to hit the ground. Now, mathematically, this equation actually goes on forever. In fact, mathematically, this equation goes on in both directions. Okay? But in reality, after a ball would hit the ground, it would really stop. I mean, it might bounce a little bit, but it, in reality, stop. Okay? So what's happening here is the mathematics work when t is 5 and t is 15. Just the reality doesn't, okay? Meaning, so when t is 5, we're at like negative 150. Maybe maybe we're over here. When 15, well, that's way down the line, so that's going to be way sort of off our chart, what we see anyways. So there is this issue with when we build models, we have to understand that we can get answers mathematically that don't work in reality. Okay? And you always have to ask yourself and check with yourself and say, does this really even make sense? In this case, would the height of a ball really be negative? Of course it wouldn't, unless it fell off a building or something like that. Okay? But in this case, that negative 150 would not work. Now, there's other things that you can be either given or look up. Maybe look up is a better word than given. But sometimes, and oftentimes, the models that you want, you can actually go look up. For instance, if you want a model in physics, well, like the height of the ball, I mean, we could go look that up. Like we just did online. If we wanted some other physics formula that gave us, for instance, conversion of temperatures, well, we can go look those up online too. Geometry. We pretty much know formulas for geometry. If I want to find the volume of a cone, where the variable was the height of the cone, or if I wanted to find the volume of a cone where the variable is the base of the cone. We could figure those things out by looking those up. Or, maybe on an actual test or a quiz, I'd probably just give those to you. Interest is another one that, we saw before that you can go look up. How much do you have to pay on your house if I change what the house is worth? Those kinds of price calculations, you can go look those up too. All right, or remember those from previous areas. All right, so let's say I'm looking at the volume of a pyramid. Now, if you go and Google and look up volume of a pyramid, you'll get volume equals AH/3. Now, the reason you get this volume as AH/3, well, you have to understand V means volume, A means area of the base, and height means, well, the height from the top point in the pyramid down to the base. Okay, so let's do a couple of examples of this. If I said, so we were given this model. And this model, you can think of as sort of like a linear model, but we have more than one variable here. So it might not be even exactly linear model. Okay, it's linear in H and it's linear in A, but we have two variables here. So it's not quite linear like we think of linear. Okay. So anyways, we have this formula. The base of the pyramid is a square, sides 30 feet, and has a height of 20 feet. What's its value? All right, so good place to start always is kind of draw what's going on. All right, we have a square base. I'm going to draw it in 3 dimensions, so I'm going to make it look like this. And then we have some peak here. And again, I didn't draw it real great, but that's what's happening. The square base, it's a 30 by 30 square. The height is 20 feet. So let me draw it this way. From there to there, 20 feet. And so if I want to find the volume of a pyramid, all right, I'm given this model, volume is equal to A times H/3. Well, first off, calculate the A, the area of the base. Well, the area of the base is 30 by 30. Right, it's a square, so to get the area of a square, you take side by side. Times H, well, we're going to times that by 20. And then we're going to divide it by 3. Okay? So take 30 times 30 times 20, divide all that stuff by 3, and you should get the volume is equal to 6,000. Now let me just say something about volume real quick. Here our measurements were all in feet. Volume is in cubic things. So we're talking about cubic feet for a pyramid. All right. So if you took a 1 foot by 1 foot by 1 foot cube, 6,000 of those you'd have to take to fill that pyramid. All right. So I want you to do this one. Again, we're talking about volume of the pyramid. In fact, we're talking about the Great Pyramid in Giza this time. So I give you this model, volume is equal to area times height divided by 3, and you answer a question that's associated with it. All right, so hopefully you did that, push pause on the video, and calculated that. So, Great Pyramid in Giza, Egypt, for those of you who don't know, is the big one, the one that you see typically on postcards from Egypt or something like that. So again, we have a square base. I'll be honest with you, the Great Pyramid in Egypt has slightly off square base, but not by very much. You can look that up on Google. But 230.4 meters on each side. And then we have this height. And again, I'm not going to draw it very well, but height of that pyramid, which is 146.3. So the volume, take the area, well, that's going to be 230.4 times 230.4. The height, 146.3. Multiply that. Divide that by 3. So take 230.4 times 230.4 times 146.3, and then divide all that by 3. And what I got is that the volume is 2,588,737.536. This would be in cubic meters. So 2,588,737.536 cubic meters. By the way, that is a heck of a lot of cubic meters of stone and rock and those kinds of things. And it is quite amazing that people back in the day moved that without any nice excavators or anything like that. So quite amazing, the feat that was accomplished by the ancient Egyptians. All right, let's look at another function that I've given here. It turns out that there's a lot of websites that you can go on and order custom like t-shirts and things like that. So we're going to look at one website in particular, customink.com. That's some place that I've used. Again, this is not an endorsement of them by any means, but it's one place that you can go online, design a t-shirt, and then order it. So let's pretend that for a certain t-shirt, the prices are modeled by the following function. Now, let me state what I'm saying here. I'm saying that X here is the number of shirts, and the output of the function is the price per shirt. Okay? So X is the number of shirts, and the output there is the price per shirt. So I want you to take that function and answer the following two questions. If you ordered 20 shirts, how much would it cost? And I want a unit price, a price per shirt, and also I want a price for the entire 20 shirts. And then if you ordered 200 shirts, how much would it cost? And again, give the unit price and also the total price. So push pause on the video and answer those questions. All right, so hopefully you've pushed pause on the video. Let me rewrite the actual function that we dealt with. So we had an f of x was equal to 4.58 times x plus 1073 divided by x plus 128. Okay? Now, if you put in 20 into that function, you should get back, well, based on how pricing works, they wouldn't give you a decimal that would round less to a penny. So the price they would give you is $7.87 per shirt. Okay. And then if I wanted to find the total price, well, since we are ordering 20 shirts, take 20 times 787. Okay. Oops, I should have done this. 7.87 times 20. And you get $157.40. All right. Now, here's the thing. If you order 200, well, what's going to happen is you're going to plug in, and I'm just plugging this into my calculator now as I speak. You're going to plug in 200 everywhere you see an X. And by basic rounding, when you plug that in, you should get $6.06. All right, again, I'm rounding this to the nearest penny. And notice that's a full, well, almost $2, more $1.80 less than the per shirt price when we ordered 20. So you get a much better bang for your buck if you ordered 200 of them. All right, and the total price, 200 times 6.06. I'll type that in, and I got $1,212 and no cents. 0.00 maybe. Okay. So you see in both cases, you ordered 20 shirts. You know, it cost you more per shirt. You order 200 shirts, it's going to cost you less. And if you ordered, by the way, 2,000 shirts, it would have cost you less per shirt as well. Okay. Now it brings up some sort of situations here. This is the pricing scenario on a lot of things. I'm not saying that it fits this function exactly. In fact, Custom Ink's pricing might not fit this function exactly, but it's fairly close. But it is interesting. You see that the more you order, the less things get. All right, and this is very, very typical of any type of business situation. If you order and you start purchasing more and more and more, oftentimes the manufacturers give you a discount because of the number of things, based on the number of things you order. All right. And there can be lots of things said about how this affects a Home Depot versus the local hardware store, or how this affects Walmart versus the local grocery store, and how that affects prices and things like this. Um, and that's maybe something that'll come up on a forum, but not currently. I don't want to talk about it right now.